Welcome to another AP Daily video. Today's topic is topic 4.5 on stoichiometry. Today's topic will include providing stoichiometry problems involving changing variables in a reaction and predicting their effects, as well as how to handle gas and solution stoichiometry. My name is Tucker Basil, and I teach AP Chemistry at Chaska High School in Chaska, Minnesota. And I'm here with the college or the high school plank, which, to be clear, is not to be associated or affiliated with the College Board. All right, a few things before we get started here. All the problems that we've done so far in class, practice problems and examples and so forth, use grams or moles. But sometimes you're given liters of a solution or liters of a gas. So just remember that in order to do stoichiometry, you need to be in moles. All chemistry happens in moles, just like the reminder that moles go into a BCA table. If you're given molarity of a solution, you're going to use this equation. Molarity equals number of particles or moles divided by the volume in liters. If you have liters of a solution, and you're going to use molar volume of a gas if it's a gas at STP. So 20, and that molar volume of a gas is 22.4 liters for every 1 mole. Lastly, if you're in that rare situation of not being at STP, you're going to use the ideal gas law, PV equals nRT, and you just rearrange that to solve for moles, because again, we need to be in moles for stoichiometry, and we would use that equation there. All right, so let's look at an example. So we have this equation, this reaction happening here. We have a student that adds 50 milliliters of some hydrochloric acid, and you have some zinc as well. The reaction occurs according to this above. When a reaction is completed at 273 Kelvin and 1 atmosphere, that's at STP, what volume of H2 gas is produced? So we're given information about our reactants, and we need to find a product. So this is a limiting reactant problem. So we're going to do a BCA table for this. Alrighty, so we're given this balanced equation here. We're also given this information. 2.35 grams of zinc. And we're also given this. Oops. There we go. So we're given both of these pieces of information, and we need to determine which of these things is going to, is the reaction going to, it's going to limit the reaction, right? We need to find our limiting reactant. So in order to fill in a BCA table, we need moles, and so we're going to use, whatever we need in order to get there. The first one is the one that we're most used to, so it's a grams to moles conversion. So grams of zinc. And the molar mass of zinc is just 65.38 grams. And so then we would just multiply those, well, divide. We get that. The next one, we're going to use molarity, but we remember that we need to be in liters in order to fill in this equation here. So move the decimal 3 places to the left, divide by 1,000, whatever you want to think about it, but this ends up being 0.05 liters. And if you remember our equation, I want to rearrange that to solve for moles, because that's what needs to go in the periodic or in the BCA table. Alright, so we have the moles of both of our reactants, so now we can plug that into our BCA table. and then start with 0 products. And so now we can finally figure out what our limiting reactant is by figuring out which of these is going to be consumed first. And we do that by taking our starting amount of moles, divide that by the coefficient. It's just going to be the same number back, right? And then for this one, we get 0.05. So we end up with 0.025. So I can easily see that this guy is going to get used up first compared to this one. So HCl is going to be my limiting reactant. And so I'm going to take this factor here, and that's going to be my multiplying factor that I multiply each of the coefficients by. Okay, and so then I come in here. Multiply by 1, multiply by 1, multiply by 1, multiply by 2, and we're going to lose our reactants, gain our products. So I don't need to calculate this because the question doesn't ask anything about zinc, so I'm not even going to bother. This one's easy though, I get 0 moles with a limiting reactant back, and really all that we care about is the hydrogen gas, so I'm going to put this. Okay, so this is the part that we actually care about. Because remember, we want to find how many liters of H2 there are. And I see I'm running out of room here, so I'm just going to make a little bit more space. So now we have we want liters. And we're at STP because the problem said that we had 273 Kelvin and it was 1 atmosphere, right? So we're going to use this. Okay, so we're given this. Moles go away. And so then I end up with this. Um, 0.56 is what my calculator says, but then I want 3 sig figs, I think, if I remember correctly. So I'll add a 0 on there. Liters of H2. Alright, so part A is complete. We calculated that. Now we want to know which of the following changes would increase if the volume of H2 gas produced, or would increase the volume of H2 produced. Okay, so now we need to remember 2 things. One, that if there's more limiting reactant, you're going to have more product. And if you add enough more limiting reactant, you might end up with a different limiting reactant. So we need to figure out if we double zinc, is that the limiting reactant or not? Is doubling the HCl, that's, you know, what's going to happen there, and doubling the concentration, what's going to happen there. So let's pop back over here. And so we want to know these things. So for I, set double 2 times the zinc, I 2 times the volume, times molarity. So the so 2 times the zinc is easy because if we look back at this here, zinc was not our limiting reactant. So if I had more of this here, like if I doubled the, the mass here, that would increase the amount of moles. And if I had more moles of zinc here, that wouldn't change my limiting reactant. So I would say no change. It's not the limiting reactant. Okay. And so now our next question is, if I 2 times the volume, that is going to change something, right? We know that that's going to probably increase something, because if I look at my, sorry, I'm just trying to get this in frame here. If I look at this, I've got 0.05 liters. And so if I increase this, if I double it, I'd end up with 0.1 liter here. And so then that would affect this here. So I'd get the 0.1 liter here. And so then I end up with 0.1 moles of HCl. I'm just going fast and loose here because we don't actually need to know what the answer is, right? We just need to know if this is going to increase our product. And so if I come over here, I would have, that would also change this here to 0.1. So 0.1 divided by 2, that'd be 0.05. So I'm increasing my limiting reactant. So if I go back to my paper over here, if I can move stuff around properly. My goodness. Okay. 2 times the volume. We increase H2 because increasing the limiting reactant. And if I increase the molarity, same thing's going to happen, right? If I go to 2 molar, I would end up with 2 times 0.05, and I'd end up with 0.1 again, and so in effect we're increasing our limiting reactant as well. So all right. So now here's another practice problem. I want you to go ahead and pause the video and see if you can do this one on your own, and then I'll share with you the answer. Alrighty, answer time. Here we go. So, this is my whole mess of work that I showed, but in the end I got 18.5 liters. Just make sure I did it right. But this is what I got for my molar mass of, what is this? Yeah, propane. That's what I thought. I don't want that yet. Here we go. Here's what my molar mass of propane was. Divided by that, I got pretty much 1. And then for oxygen gas, divided by its molar mass, got this. Put those numbers into my BCA table. It looked like propane was going to be the limiting reactant, right? But oxygen gets used up 5 times as fast. So in accounting for that, we end up with oxygen as our limiting reactant, and this is our multiplying factor here. So then I multiplied that by each of my coefficients, even though the ones I only really needed was carbon dioxide. And so I end up getting that I make this many moles of carbon dioxide, 0.8269 moles. So then I took that down here. I left more space for myself this time. And it was at STP, so I was able to use the molar volume of a gas here. So just multiply by that, and I got my volume there. And then I asked, what happens if you double the propane? Well, nothing happens because it's not the limiting reactant, right? If I have more of my excess product, or excess reactant, then whatever. I guess I just have more propane left over. But if you double the O2, you're going to have an increase in product. Alright, so what are our takeaways here? So use the molarity equation for liters of a solution if you need to. Use molar volume of a gas for gases at STP. And then use PV equals nRT if you're not at STP, and you just rearrange the equation like so. Thank you for watching, and have a great day.